So in the class we started designing a sequence detector with overlapping patterns, and we wanted a mealy state machine for this. And we went over the state diagram procedure, got a state table, we tried state reduction, and we found that no state reduction is possible. And then we did the state assignment, and after doing the state assignment, we were wondering how to design the circuit from this using JK flip-flops. So we created a excitation table, and we said that we'll fill this excitation table up, and that we'll use this excitation table to get the JK inputs. So let's do that process here just for completion. So I will create a new page and have it copied here. Make it a little bit smaller to fit everything. Delete a bit of stuff here. Okay. And also we have this table with w equal to 0, w equal to 1, and we have 3 flip-flops that we want to design on. Okay. And we have our JK excitation table to refer to. We can also copy this to the next page that all our information is here. So wherever we have Q going to Q bar, we enter the right values there. So here for Y2, we have 0 to 1, so we enter 1D here, 1 to 0, D1 here, and 1 to 1, D0. 1 to 1, that is 0, 0 to 0, that is 0D, and 1 to 0, that is D1, and 1 to 1, that is D0, 0 to 0, that's 0D, and then 0 to 0, that's 0D. This is 0 to 0, that is 0D. We need to get 0 to 1, we need 1D as an input, and to get from 0 to 1, we can have 1 to D. Okay. And then we can do the same thing for W equal to 1. To 0 to 0, we need 0D. For 0 to 0, we again need 0D, and then from 1 to 1 we need D0. 0 to 0, 0D, 1 to 0 we need D1, 1 to 1 we need D0, 1 to 1 to 1 we need D0, 0 to 0 to 1 to 0, 1 to 0 we need D1, 0 to 0 we need 0D, and 1 to 0 we need D1, 1 to 0 we need D1, and then 0 to 0, 0 to 0, 0 Ds. 0 to 0, 0 to 0 we need 0D, and 0 to 1 we need 1D. Okay. So this will result in 8 K maps, 12 K maps, 3, 3, 6, and twice 2 times. We'll need 12 K maps, and then more K maps for the output. So we can actually develop a shorter procedure for this. We can directly read off this from a K map for the next state, but for now let's do this for J2 and K2. Let's create a K map for J2, and we have inputs as W, small y2, y1, and y0. And we have min terms 0, 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So for w equal to 0, this half, when our present state is 1, then J2 is 0. When it's 3, our present state is 1. When it's 0, then it's 0. And in the other two cases, it's D, and in rest of the cases, it's just D. Why is it D? Because we have a closed state diagram for all these states, so we will never go to the other states that haven't been encoded. So we only need to fill in for J2 equal to Z, J2 corresponding to 1, 3, and 0. So fill those up, and then we have a lot of don't cares. For W equal to 1, we also need to fill only those three. And for w equal to 1, you can add 8 to it, and you'll get those min terms number. So we need to fill up 9, 8 plus 3, 11, that is also 0, and it was 0, 8, that's also 0, and everything else, including these two, I don't care. So to develop a shortcut from next state K-map to J to K2, let's also draw a K-map for the next state part. And this is K-map for Y2. We have inputs W2, W1, W0. Okay, and we can fill up min terms. We have for 1 we have y2 as 0, for 3 we have y2 as 1, for this is 5, this is 4, for 5 we have y2 as 1, for 4 it's again 1, and for 0 it's 0, and 2 and 6 never, 2, 6 and 7 never occur, so they are D's. Okay, and then we have a K-map, the K-map for K2. K2, and we can we need to fill up the full y2. We didn't fill up the w equal to 1 part, in which case apart from the d's, once here is a mirror image, we just have 0, 0, 0, 0. Okay, so we can fill up K2 by looking at this column and this column. So wherever there were D's in J, we get 0 and 0 for far, and wherever we fill up J, we get D's. And then we obviously have D's, where y2 is D, we get D. And for w equal to 1 part, we get 1 here and D. D 1's for 12 and 13 and D is for everything else. So what are we observing here? So here we in J2 we only have 1 1, a lot of zeros. So we can group this and get J2 as W bar Y1, and here we have a lot of ones and zeros. We don't need to group both of them, so what we could write in terms of either of them. So here we get K2 as W Y1 bar. Okay. K2 is equal to. So can we get these groups directly from Y2? Can you read this off directly from Y2? So can we do this step and these steps directly from the Y2 K-map? So one thing we'll need to note is that this entire thing Y2 depends, the numbers in here are the next state, and this half, these two cells, right? So we are talking about capital Y2 and transitions from Y2. So we are interested in what happens when Y2 goes to capital Y2 and what should be the value of J2 and K2 to enable that. So, so in this half of the K map, Y2 is always 1. And if there are ones for Y2, the K map, that means we are going from 1 to 1 and 1 to 0. Right? And we have the values for that, D0 and D1, right? And then we have Y2 equal to 0 part of wherever capital Y2 is 1, then we are going 0 to 1, and that needs 1D, or 0 from 0, that needs 0D, right? So when we are in the Y2 equal to 1 half of the K map, we can directly, we don't care about J2 at all, and then this entire half. So to design the J2 part, we can only focus on this red half of the K map, and same is true for the K for designing the K. In the red part, K2 will always be D, so we don't care about that, and we can only focus on K2 equal, sorry, blue part of the K map. And the in this part, blue part of the K map, the values of K's are flipped from what we have for Y2. So, depend upon that, so we can directly write K2 as W. We here wrote it as WY1 bar. We could have also written it as just W. And here we can imagine everything to be D in the entire thing and group the K2. In this part we can so that will give us the formula for K. Now we want J2, so this should be 0. Okay, so we went over step-by-step process of figuring out what J2, K2 should be using the excitation table. We filled out the J2 K-map and K2 K-map, and now we seem to be reaching to some more simpler rules that can give us some kind of shortcut to come up with J2 and K2 K-maps. So what we are going to do is we'll try to apply these new rules to our state assigned table and see if we can do this more efficiently. So we have this state assigned map here, and so we made a K-map for Y2 already. And let's try to do the same for Y1 and Y0. So that's too messy. I'll just make it from scratch. So let's use black. Okay, so we have Y1 here, and we W for these two columns, Y2 for these two columns, Y1 for these two columns, 0 for these two rows. And then we refill these up. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Some numbering for the state. Midterm. So we are looking at y1 for w equal to 0 and y1 for w equal to 0. So let's fill this up. So when w is equal to 0, and this half of the map, when present state is 1, y1 is 1, when it is 3, then it's 0, when it's 5, it's 0, when it's 4, it's 0, when it's 0, it's 1. Okay, and then we have d's here, and then we add 8 to it to get w equal to 1. So in 9 it's 0, on 11 it's 0, on 13 it's 0, on 12 it's 0, on 8 it's 0, otherwise it's D. So let's write down the excitation table again for JK. So we have 4 possible transitions that we might want, and when the present state is 0, the K becomes don't care, and J is same as the next state. And when Q is 1, then present state is 1, then K becomes don't care, and we flip the J. Right. So here we can create very simply J and K maps from y1. How? So to make the J1 map, wherever y1 is 0, wherever y1 is 1, we make it to be don't care. So here we are concerned about this y1, so we make wherever y1 is 1 to be don't care. And for K1 map, where y1 is 0, that becomes don't care. So all of this half of K map becomes don't care. And wherever there was 1, and zeros become 1, ones become 0. Okay. And this just gives us K1 is equal to 1, and this gives us J1 as this big group, which is W bar Y2 bar. Okay. We can do the same thing with Y0. So let's copy this once again. to a new page. And this time we are interested in K-map for y0. So this is the K-map for y0. We have W, we have y2, y1, y0. So we fill this up using momentums, labeling, and then we have we are looking at y0 this time. On momentum 1, w equal to 0, we have y0 is 1. For 3 we have 1. For 5 we have 0. For 4 we have 0. For 0 we have 1 again, and the rest of them are don't care. And then we look at w equal to 1 half of the K-map when min-term is 1 plus 8, 9. We have 1, 3 plus 8, 11. We have 1, 5 plus 8, 13. We have 0, 4 plus 8, 12. We have 0. And at 8 we have 1, and the rest are don't care. Okay. So this time we are looking at y0 and y0. So recall, when we are going from y0 to y0, we are going for k is equal to don't care and j as the same as capital Y0. And when we have y0 as 1, we are going for j as don't cares and k to be flipped. So this half the K-map and this half of the K-map will lead to different answers. So we can make a K-map by creating a copy of this for 2 copies of this for J0 and K0. So here let's create this for J0. So and this one is for K0. So wherever y0 is 0, wherever y0 is 1, j0 is going to be don't care. So y0 is 1 here, so all of these will become don't care, okay? And the rest of the K-map remains the same. So here we can write j0 in terms of these 2 big groups, y2 bar. And for K0, uh, what we can do is wherever y naught is 0, there we have don't care. So we'll convert this to don't care, don't care, don't care, and these are already don't care. And we also notice that we can, we have to flip the y naught to get k naught. So we replace ones with zeros and zeros with 1, zeros with 1, and ones with 0, ones with 0, 1 with 0. So now we can have k naught as just one big group of y2. Okay. So we have expressions for J2, J2, K2, J1, K1, J0, K0, and what is J2, K2, W bar Y1 and W bar Y1 and W, and for J1, K1 we have W bar Y2 bar, W bar Y2 bar, and K1 is just 1, and for J0 K0 we just have. So how does the circuit for this looks like? We can move this aside, and then we can draw three JK flip flops, and for J2, K2, J1, K1, Q2, Q2 bar, Q1, Q1 bar, J0, K0, Q0, Q0 bar. Okay. And we have some clocks coming in, and we have W coming in, and you have a single AND gate for J2. For K2 we just given the W input. If we have WR, let's say we have WR, and here we get given Y1, which will come from here. We can connect that, but that will make things ugly, so I'll just keep them labeled here, and this is Y0 for This is just 1 for here's y2 bar, so we can just feed in y2 bar to j2 and k naught, we just have y2. Okay, so there's still one more part of the circuit remaining, and that is the output. Now, so for that we create another page and go back to our state assigned table. Create a copy here, and we have outputs that we need to copy here. So the outputs for w equal to 0 and w equal to 1, and let's call this z. So we have 0, 0, 0, 0, and we are trying to detect here 0, 1 and 1, 0. Okay. So this is relatively simple. We draw a variable k-map. W, y2, y1, y0, and we have 0, 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, and so this is 1, 3, 5, 4, 0, 1, 3, 5, 4, 0, don't care, don't care, don't care, or 9, 11, or 9, 11, 13, 12, 8, 9, 11, 13, 12, 8, don't care, don't care, don't care. So Z can be represented, there are only two ones, and they have all neighborhoods of zeros. And a lot of D's. So if you write them down here, W bar y2 bar, y1 bar, y0 bar plus w y2 y1 bar, y0 bar. And you can also take out stuff common like this, and then you can say this is sorted of something. And then we can go back to our circuit and have an AND gate that gives us Z, have a XOR gate between W bar and Y2, W1 bar, W0 bar, going to C. So this W bar can be connected, whatever, or not. And this is our circuit. Thank you.